Hello, we're going to do a quick review of resistance, including the four factors that affect it and Ohm's law as well. Resistance is a measure of how hard it is for electrons to move in an electrical circuit. So you can think of resistance as being like friction of the wires. So we'll have a wire and we'll have our positively charged metal ions, and then we could have our electrons traveling through. And as they go through, they're going to be bumping into these metal cores. And that's going to slow them down, just like friction does in real life. Also, what resistance does is it generates heat, just as friction does as well. There are four main factors which affect resistance. We're going to talk about, in this class, the material, or the resistivity, rho, of the material. The cross-sectional area of the wire, which is just like a thickness, the length of the wire, and finally the temperature of the wire. And these again are the four factors which affect. And we can incorporate three of these factors into our resistance equation, which is on a reference table. You can find that our resistance is equal to the resistivity, rho, times the length over the cross-sectional area, A. And again, these variables are R for resistance, which is measured in this unit ohms, rho for resistivity, which is measured in ohms times meters, length, which is measured in meters, and cross-sectional area, which is measured in meters squared, because it is an area, the area of the wire. So if I have the wire coming down and I cut it in half, this region is going to be my cross-sectional area. And again, really important, the units of resistance are ohms. Ohms, it's a new unit, but you need to get used to it. So we're going to discuss how each of these factors affects the resistance. So the length, when we have a longer wire, we have more resistance in the circuit. And this is because when electrons are moving through the circuit, they're going to collide with metal ions. And when they're colliding, they're going to slow down, so there's a resistance to their flow. When the wire is increased longer, the electrons need to travel further, so they have an increased chance of the collision. Cross-sectional area is another geometric effect, but it's a different thing. We have when the cross-sectional area increases, the resistance of the wire decreases. And you can also think of this in terms of the equation, and because in terms of our equation, if A is going down, resistance is going to go up. So, and this happens because when you have more area to travel through, you have less of a chance of colliding with the metal ions, so you will flow more easily. So resistivity is probably the hardest of the three to describe. In this case, it's a material property which determines how easily electrons can flow through material. Think about the difference of conductivity between rubber and copper. There's obviously a very big difference, even if we have the same size wire. And this is because copper has a much higher resistivity, rubber has a much higher resistivity than copper. And again, resistance has geometry incorporated while resistivity does not. You can find resistivity values on the bottom of the reference table. Again, each specific material has a specific resistivity value and is measured in ohms times meters. Those are the units. Again, these guys are your friends. You need to remember these in the problems. They might say they're copper or there's gold, so you need to know the resistivity value at 20 degrees Celsius, a specified temperature. If a component of a circuit obeys Ohm's law, then increasing the temperature will increase the resistance of the material. This is because the positively charged atoms are going to vibrate around and bump into the electrons. You could think of this as walking through a club. People are dancing all around, and you're just trying to get through. Take a second and check your understanding. I'm going to go through this quickly. You might need to pause and do this because I'm going to speed through it really quickly. The first question is true. The second question is true. And here are all the answers. We're going to go through a quick practice problem. We know that we have a 0.868 meter long wire, cross-sectional area of this. We have a resistance of 0.125 ohms at 25 degrees Celsius. And so we need to figure out what it could be made of. And so really what it's asking us is to solve for the resistivity, and then we can figure out what material has that same resistivity. So we know the length is 6 meters. We also know these values, and again we're looking for resistivity because it's talking about materials, and we know the resistivity of those materials. We go back to our equation. We have R is equal to rho L over A. Then we're going to solve for rho, multiply both sides by A. Solving this, we get a value of rho equal to 0.1234515 ohms. Looking at our reference table, we see that a object with this value is nichrome, so the material must be nichrome. Again, you have to go back to your reference table and relate this resistivity to nichrome. Here we have a more straightforward problem. We're looking to find the resistance of a 1 km length of nichrome wire with a cross-sectional area of this at 20 degrees C. So we're looking for the resistance. But in this case, the tricky thing is the length is 1 km, but we need it in meters. Going to a reference table, we find that's 1 times 10 to the 3 meters. We know that the cross-sectional area, A, is equal to 3.5 times 10 to the negative 6 meters squared. And going to a reference table, we find that rho for nichrome is equal to 150 times 10 to the negative 8. Finally, we just use our equation. Rho equals R equals rho L over alpha, over area. And solving this, we get that rho is equal to 4.28 times 10 to the 18th, which is crazy big, ohms. Now we're going to discuss Ohm's equation, or Ohm's law, which is given by the equation R equals V over I. So a good way to think about Ohm's law is with water. So let's say we have a bucket of water, and the bucket has a spigot on it, so just to let the water out. So we can think of these parts of Ohm's law as like parts of this spigot. So because there's water in here, it's going to be flowing outwards. You can think about the water, the rate of water coming out of the spigot, our current. Let's also assume that we have a big piston on top of our, let's say that we also have a big piston on top of the water, so we can press down with force and increase the water pressure. We could think of this as being the potential. And finally, if we think about this hose being able to be constricted, then this would be our resistance. So we're going to be discussing this in class as well. Again, it's helpful to visualize it physically instead of just thinking about it in terms of electricity. Again, this is straight from our reference table. We know resistance is equal to voltage divided by current. And again, the key thing here is that resistance is measured in ohms. So we're going to work on a problem using this formula. So we have electric circuit consists of a variable resistor connected to a source of constant potential difference. If the resistance on the resistor is doubled, the current is what? So because we're trying to find current, and we know we're talking about resistors and voltage, this makes me think of Ohm's law right away. V equals I over R. Resistors. But because I want to see what's actually happening to the current, I want to manipulate the equation to get current by itself. Is the thing that's what I'm going to do. We want to get it by itself. So I'm going to manipulate the equation to get current by itself. This crosses out. Then I have I R is equal to V. So then I'm going to get it by itself by dividing both sides by R. R's cross out. And then that gets me that I is equal to V over R. Now we know that the resistance is doubled. So let's do I is equal to V over 2R. And we also know that there's a constant potential. So looking at the numbers that fall out of this, we see that the fraction is 1/2. So the current is going to be 1/2 as great. It is going to be halved. So let's think about the graphs of Ohm's law for a second now that we'd apply this equation. So we have a graph of voltage versus current. Ohm's law is going to be a straight line when the resistance is constant. So we should look at our slope first. So we know that the rise is volts and our run is current. And so the units or the equation of our slope is voltage over current. So the slope in this case is going to be R. So this is where it gets a little tricky. When we have a graph of I versus V, the slope of the line is going to be I over V. And so this is going to be I over V. Resistance is only equal to voltage over current. But what we could do is we can take the inverse of both sides of this equation. And this has a function of flipping both of them. You can imagine R is over imaginary 1. So V over I flips. And also it's going to be 1 over R. So the slope of this guy is 1 over R, while the slope of this guy is just R. One more problem. We have an electric current consists of a variable resistor, so the resistor can change, connected to a source of constant potential difference. Which graph presents the relationship between the current and the resistance in this circuit, so the relationship. So always when you see graphs, go back to thinking about an equation. So we have current, resistance, and it talks about potential difference, which is voltage. So we think of Ohm's law. R is equal to V over I. But we know that current in all of these is in the y-axis, so we want to get current by itself. So we're going to manipulate our equation again. And going through this, we first multiply both sides by I. The i's are going to cross out. Then we're going to take I over R is equal to V. And we are going to divide both sides by R to get it by itself. And that gives us I is equal to V over R. But what we need to think about now is, in terms of the graph, what is being graphed here. So again, we can think about our I as our Y, and because the resistor is on their x-axis, we could think of it as over X. We know the potential difference, or the V, is constant, so we could call it C. The graph of Y is equal to 1 over X is the same as these two. If you graph it on your graphing calculator, it has this swooping curve. So the answer is going to be -1. Excuse me, the answer is going to be number 1. That is all I have for you today. I hope this was a helpful review. I hope it wasn't too long, and have a great day.